Hey y'all, it's Dr. Powers. So we're going to look at surface integrals. So here we have a parametric surface. We parameterize with u and v, and we want to integrate some function over the surface. And so the idea then is this is how you can calculate. For example, I mean you can see this is I'm jumping straight to the formula. So the surface integral over the surface S of some function f of x, y, z is the double integral of this function times the the magnitude of this cross product. And you should observe if we plugged 1 in for the function, if we're integrating the function 1, then we're actually calculating the surface area of this object. That's the same formula we saw in the previous lesson. And so this is related to, I mean, you can kind of see the relationship from line integrals to arc length. A line integral is, an arc length just is the line integral of the function 1. Right. So anyway, we'll take a look at an example. Let's look at the surface integral of x squared over this unit sphere that has a radius of 1. So we've already seen how we parameterize the unit sphere, right? We're going to have we're going to r is going to be the sine of v, the cosine of u, the sine of v sine of u, and then the cosine of u, right? This is the spherical coordinates where we have u going from 0 to 2 pi. That's kind of our theta, right? And v going from 0 to pi. The radius is 1, so I'm not showing the rho equals 1 in front of all of these. So when I calculate this r sub u, this is going to be negative sine v sine u. We're going to have sine, then we're going to have sine v cosine u, and then we have the, it should be the cosine of v, not the cosine of u. Let's fix that. Cosine of v. Then we're going to have 0. R sub v, we're going to have the cosine of v cosine of u, the cosine of v sine of u, and we've got the negative sine of v. Now, if you recall from before, when we found the magnitude of RU cross RV, it actually turned out to be something pretty simple. It ended up before being, it was a squared times the sine of v. But in this case, the radius is 1, so we actually don't even need that portion here. So it's just the sine of v. So back to what we're actually trying to do here. We're going to be integrating over our domain D, our 0 to 2 pi for u, and then 0 to pi for the v. Then we're going to have, our function is x squared. So x is the sine of v cosine of u. So I'm going to put that right here, sine of v cosine of u. And then I'm going to put times the sine of v. And then I'm going to have my du and dv. I only put x in here. It's x squared, so it should be sine squared v and cosine squared u. So back to this, right? This is going to be the integral from 0 to 2 pi of the cosine squared of u du, and then the integral from 0 to pi of the sine cubed of v dv. Now, we've done enough integrals at this point, so I'm not going to spend too much time here. I know that the area of the cosine squared of u is going to be pi, and the area under the curve of sine cubed from 0 to pi. I'm going to just kind of cheat a little bit and get the answer for this. Yeah, this comes out to 4/3. And so what we're getting at, of course, is 4 pi over 3, the surface area of a sphere of radius 1. So now, if the natural application for something like this is if your function of x, y, and z is a density function, and you want to calculate the mass or the center of mass of a kind of a deformed sheet of metal or some sort of hollow hollow shape that has non-constant density on this surface, this is a very useful kind of. I mean, that's the most straightforward application of something like this. I'll just say that. I'm not going to do an example of that right now. I just wanted to make you aware of this kind of application. And so if we're doing a surface integral over on a surface with the surface where z is actually a function of x and y, so it simplifies because as you know the magnitude of the cross product from the previous lesson simplifies to this, and so this becomes our more simplified formula for the surface integral. So let's take a look at this, where this surface integral over this region, the surface is z equals x plus y squared, where x is going from 0 to 1 and y is going from 0 to 2. So we already have we don't need to change this into a parameterization of u and v, because x and y are fine for our two parameters. So the function is y, and so we're just going to have x going from 0 to 1, y going from 0 to 2. Y is our function of x, y, and z, right? Which is g of x, y, which is x plus y squared. There's no z in my function in the beginning, so there's nothing happening there. I just need to put this square root of 1 plus the partial with respect to x is going to be 1, so that's 1 squared. The partial with respect to y is going to be 2y, so that's going to be a 4y squared. And I'll put my dy and then dx here. Well, the nice thing about this, of course, that there's no x, so I can actually just kind of ignore that. X, the integral from 0 to 1, I would multiply this thing by 1. That's not going to change anything. And what I've got here now is y times the square root of 4y squared plus 2. I'll put a dy there, and I'll do a substitution here where I'll let u is 4y squared plus 2, and I'll get the du. That's going to be 8y dy, and of course my y dy would be 1/8 du. My bounds, u of 2, my upper bound is going to be 4 times 2 squared. That's 4 times 4, 16, plus 2 is 18. U of 1 is going to be just 2, so I'm going to get a 1/8. I'll put it right here. So we're going to go from 2 up to 18, and the y dy, that's going to be my du along with the 1/8. That's part of it. And then I have u to the 1/2 power. So we're going to get 1/8 u to the 3/2 and a 2/3 right here. we're going to go from 2 to 18. And so we're going to get, let's see, 2 times, that's going to be 1 over 4 times 3 is 12. 1 over 12 times 18 square root of 18 minus 2 square root 2. And 18 square root 18 actually is 18 square root 18 is actually, I can factor out the 18 is 9 times 2, so I can take the 9 through and that becomes another 3. 3 times 18 takes me to, that's going to be 6, that's going to be 54 square root 2. 54 minus 2, that's going to be 52. So I'm going to get 52 square root 2 over 12, and I can divide everything in half. Sure, why not? That's going to be 26. Well, I could divide it by 4. So 54, it's going to be what? 13 root. Okay, so you've been exposed to the kind of formulas for calculating a surface area, and I mean, calculating center of mass and is just the same as calculating center of mass for other kinds of objects. So, but you can. I'm not going to cover that right now, but this is enough to kind of get you exposed to it, so you can know what surface integrals are all about. That's it for now. All right, bye.